That's the difference right there, delta x. I want to know what the value of this function is at delta x from x0. Okay? Everybody see that's the question? That's what Taylor Sears is trying to do? Well, look what the claim is. The claim is f of x0 plus delta x is equal to f of x0. So it's this amount, right? There's f of x0. And then what do you add to it? Okay, the derivative at x0, which is the slope of the tangent line at x0. Okay, so if I drew in a slope of a tangent line at x0, it would be like this. Right? What's the slope of this line? The slope is equal to df dx at x0, right? That's the slope of that line right there. Now, if I take that slope and I multiply it times delta x, what do I get? You get the rise right here. So that amount is df dx at x0 times delta x. And, yeah, can you see what's happening? You're starting to literally build that function based on all the knowledge of that function at x equals 0. Can you see that? All right, that's the physical interpretation of a Taylor series expansion.
And each term brings it closer and closer.
Each term gets you closer. So here, in math, they probably didn't teach you that picture, right? I don't know if they did or they didn't. This is the picture that I always remember. And so it's no surprise to me how a Taylor series expansion works, because this is the picture I have in my head. Yeah?
So you can build any function by just knowing that one thing.
Yes, that's right. Yeah, that's what that expansion is. Yeah. Okay, so let's continue to do the Taylor series expansion of this type of curve of potential. So that's very nice to know. You guys should have it in your head. You should be able to recreate that so you understand it.
Can you recap that one more time, please?
The goal is to find, you're trying to find out the function at some point x0 plus delta x, where you know everything about the function at x0.
Yeah.
So I say, well, okay, I know everything about the function x0. I want to find the function up here. All right? Well, the function up here is up here. And so you can see that it's literally f of x0. That gives me that amount. Right? Plus, if I take the derivative of f with respect to x and I evaluate it at x0, that gives me the slope of that line at that point.
Right.
And if I multiply it times delta x, then I got that little height right there. So now if I add f of x0 plus this thing, I'm all the way up to there. I'm almost up to the true value.
Okay, and the next point?
You get closer.
So you're
How
ready.
low? I can see, like, I can understand when you take the derivative. What's the second derivative going to look like?
The second derivative has a meaning too. All right? But this expansion, the next term is going to be, you could draw it in and get a little bit closer.
Because you're adding the second
That's
derivative.
right. You're adding in all these terms. And so if delta x is very small, then this is just approximately f of 0.
So you're using the vertical component from that part right there on that triangle to equal this potential, right? Is that what you're
So that's what this is. What f of x0 is find the vertical part at x.
Yeah.
x0 plus delta x.
Right, and then you get that vertical part, you can get the potential in terms of
Okay,
that.
so yeah, I'm using the same idea as here, but I'm going to get to something a little different. Okay? So a Taylor series expansion of the potential is going to be the value of the potential, right? Plus the derivative of the potential evaluated at x0 times delta x. And then what's the next term?
Second, 1 over 2. So
Plus 1/2
second derivative.
second derivative of d of x with respect to x squared evaluated at
x0
x0 times
delta x squared.
delta x squared plus I'll just higher order terms.
It varies with the
So factorial on the bottom.
factorial, right?
Yeah, yeah. I mean,
Okay.
2 factorial is 2. Right?
But the next term will be 1/6
Yeah. Okay.
times delta x cubed.
Yeah.
And then,
Okay. So look, potential energy. It's energies. What matters not is the absolute value of potential energy. What matters is difference in potential energy. So everybody agree?
Yeah.
Because it does. It matters like You could fall from a hill, so here, I fall from here to here. Does it matter if I fell from here to here, or if I fell from here to here? No, so it's the potential differences that matter. So what I'm going to do is I'm going to arbitrarily call that potential a 0.
Right, because it's constant.
Why not?
Right.
I can do, it's a
Yeah,
scalar.
it's in every term.
It's a scalar energy, it's in every term, it's going to be subtracted away. Okay. What's the derivative of this potential with respect to x of a harmonic oscillator? Look at the picture. It's 0. Why?
Because it's at the lowest.
It's a minimum, right? Add the derivative right there is 0. So what happens to this term? It
point.
goes away. Okay? Therefore, v, and let's no longer say about x0, we'll just say v of x, but about this arbitrary. V of x is approximately equal to 1/2 stuff times x squared.
It
Right?
makes sense because it's like a parabola.
Okay, and why not call this a k? Right? Let's call this second derivative term a k. So it's 1/2 kx squared. And so what does that potential energy look like?
Potential of the spring.
Spring.
That's the spring potential, that's the energy of a harmonic oscillator.
That's because it looks like a parabola.
So that looks like a spring potential.
Would you call K? All the
Whatever's-
second derivative, love crap.
All right? Everybody, what's that?
You just call the second derivative K.
K, yeah. It's got to be some value that looks like a spring constant, yeah?
So when you say like find it about x0,
Yeah.
like we're making x0 the minimum.
Yes. Yeah, we're gonna, wherever x0 is, we're going to call that a minimum.
Okay, so we can cross. So the reason we crossed out the first one and the second one is because we know since it's the minimum, the derivative is going to
Is 0.
Zero.
Has to
So
be 0.
we just know that. So
Yeah, and this one, it's a scalar potential. What happens is, what matters is differences in energies. So why not call that 0? Because we're going to be doing differences anyway. So you're left with 1/2 the second derivative times x squared. But this looks a hell of a lot like 1/2 kx squared. It looks like a spring. All right, so this means, okay, so in other words, we've got a spring. Right? A spring
Simple harmonic oscillator.
in the simple harmonic oscillator. All right, now here's the scoop. When you're in this type of potential energy, what type of equilibrium, and it's definitely an equilibrium. Is it a stable equilibrium or an unstable equilibrium?
Right there.
Okay, it's stable. Here's the scoop. When you're in a stable equilibrium, you're at a bottom, and if you displace a little bit about a stable equilibrium, you wiggle about that equilibrium. That's what a stable equilibrium is. All right, but could I be on the top in an equilibrium? Yes. But if I
Stable.
touch it and displace it a little bit, do I wiggle about that equilibrium?
No,
No, I fall catastrophically away. So that's an unstable equilibrium. Okay, so here's the next point. If you see systems that are in stable equilibrium, meaning that when you hit them, they don't catastrophically fall away, what can you describe their energy, their potential energy as?
1/2 kx.
Spring. It's like a harmonic oscillator. So whenever you see stable equilibrium, a system like a table made out of a whole bunch of atoms stuck together, it's essentially in stable equilibrium because it's not falling away. And therefore, what can I describe as the thing that's holding all these atoms together? A spring. It's like they're bound by a spring, and it has a potential energy like 1/2 kx squared.
So, like a marble inside of like a bowl.
Yeah, stable equilibrium.
Right. So that's almost like I almost look at that pitching me through at almost.
That's it.
Yeah. And then essentially you're talking about it moving on a parabola.
I'm not talking about any movement. All I'm saying
It could
is
be
that
modeled as a parabola. It's moving along the lines of a parabola.
I think we're adding too much to it.
Okay.
A marble in the bottom of a bowl will wiggle about that bowl.
Yes.
A marble on the top of the bowl can be in equilibrium, but if you will, it'll fall off.
Right.
So now I know that when I go out and I look at systems that are in stable equilibrium, I can model the potential that they're in as being in a harmonic oscillator. So how many things around us are in stable equilibrium?
Mostly everything.
Just about everything. So is this an important potential to be able to approximate things as? Yes. So when you do solid state physics and you model like atoms being stuck up from other atoms, guess what the potential looks like? Okay? Yeah, like that thing.
But when you, I don't even want to know,
Just
but
the K changes.
when you're doing solid state physics and there's 10 to the 23rd springs,
Yeah.
that's just, I mean,
You take a statistical distribution of 10 to the 23rd spring.
You become very clever. You make it 10 and you make them in a loop and you make the conditions like if you're 10 to the 23, when I shake this guy, I shake that guy, I shake that guy. Right? That looks just like if you put him in a loop of 10 and it goes around. And then what you do is you do it for like n finite and then you let n get big. Alright, so you're clever, but it's all these same ideas. It's these ideas that you just extend up. And the other thing is that when I always talk to people about how to solve problems is you never solve the hardest problem first. What you do is you solve the easy problems and you gain insight, right? And you gain feel. And then you start packing on the complexity.
You just treat it as a massive point elephant.
Yeah, exactly.
Point of mass elephant.
Yeah,
and
well,
go from
I
there.
mean, the example I give is you never solve solving carbon first. What do you solve first?
Hydrogen.
Hydrogen, and you build up the carbon from there.
Hydrogen gives you helium, and helium gives you lithium.
Things like that, yeah. All right? Okay, so we didn't get as far as we wanted again, but
Sometimes it's easier just to
not
straight
my
down.
fault. All right, we
You only
got
deal with that one
through
specific
this
spot,
details
that's it.
very well. And we are definitely going a little slower than I thought, all right? And so we will have to do a class to make up and catch up, all right? I didn't think I'd have to do that problem in so much detail. I'm throwing in some other detail, that's just the way it goes, all right?
do we on schedule something or tentatively?
Yeah, I mean, I want to get done what I said I'm going to get done.
We're missing Tuesday too.
Oh, God, we're definitely going to have to make up a class.
Well, it's on Tuesday.
It's
Monday. It's going to take a Monday.
When's that happening?
I think next week. I'm going to school on Monday.
The day after the Monday.
I'm like, I just work 24/7, so I don't know.
Yeah, I never know.
Holiday coming up?
Yeah,
Yeah, Monday.
Monday's a holiday.
So no class on Monday. So, and then
What's
so
that?
we're losing this class.
Today, celebrating.
What I usually do is I have an evening class sometimes. If everybody can make the, Matt, you
The
can.
only night I do is Monday night.
Okay, so maybe I'll do it on Monday night.
What
And
time?
I can do I have scheduled myself every Monday night off.
Okay, so
Like,
maybe
what
we'll do
time
it on
would
Monday
you-
night, and we'll make up like 2 classes on a Monday night.
gonna say.
Like 4 to 8?
Yeah, I could do something like
I
that.
can do any
Depends.
time from 6 a.m. to midnight.
Okay, so maybe we can do it on Monday afternoon. What we'll have to do is talk about it.
Not this coming.
Here's the scoop, is I'm almost better.